Hello guys, this is another example for vertical circular motion. Now let's analyze this example. Here you can see that a particle is placed on the outer surface of a smooth sphere of radius r. So the radius of the sphere is r and is gently released, right? So initially it was around here, gently placed, and gently will be released. So it will slip down the surface. Then initially it was positioned at a distance h. So I forgot to mention it is vertical distance. That means from the center it is about h height, right? It's about h height, and this is the position. So the vertical height is capital H. And find at what height the particle will leave the sphere. Now, this is a good example for a particle in a circular motion which is not tied to a certain fixed point. So, in other cases, like when the particle is tied to a fixed point by a rod, or when it is moving in a circular path like a pebble, in that cases, the particle will have to follow through the curve, right? But in this case, it is not tied to the surface. It just kept on the surface and let it release. It will release and it will slip down the curved surface. And there's a chance that it will slip off. Now, obviously, it will slip off the surface, right? So this is the initial position. This would be a general position. So we have to mark a general position. So after that, we have to uh, show all the forces acting on this. So one of the external forces would be its weight, own weight, mg, and another external force would be the reaction r, reaction on the particle by this smooth surface. Now I have shown here an angle with respect to this vertical line to this position. This is theta, therefore this is also theta, right? So at this point, let's say that when it is released initially, gently released, that means the particle initial velocity is 0, then it will acquire a certain velocity when it arrives at this position. Let's call it v. Let's call it v. Okay, v velocity. So that means towards the center, you will have v squared over r, centripetal acceleration. The tangential, you have dv by dt. So we have derived this dv by dt. Okay, so let's look at this, and what we have to do is that we can use F equal ma, right? We know the centripetal forces. Then centripetal force would be mg cos theta in this direction and minus r in that direction, and the acceleration should be v squared over r, right? So we'll also when it is released from this position, and when it comes to this position, you can see that the height will change, right? There's a change in height. Changes in height means there's a change in potential energy. Change in potential energy means there's a change in kinetic energy. Kinetic energy change means there's a change in the velocity. So that way, using the energy conservation law, because now to this motion, this is the only external forces are. So we don't account weight for this, because weight is accounted for the potential energy change. So any other external forces, this is the only force, external force acting on this particle, but this will not influence this velocity, because this is perpendicular to the direction of motion at that point. Okay, so we can use the energy conservation law to find the velocity when it is at this point. So you can see that there's a height change. So let me call this height at this general point by h. Using energy conservation laws, uh, energy conservation is conserved. Therefore, we can use right. So energy is conserved. That means at the starting point, let's take this to be the reference line. This is the reference line above anything is considered positive potential energy. So this would be mg capital H, and at this question, the energy of the total system would be half mv squared because it acquires velocity, plus this should be mg simple H. So I have mentioned simple H is the vertical height. This vertical height is what matters for the potential energy change. So now based on this equation, we can obtain V squared equals 2G capital H minus simple H. Right. Now the next equation for this would be F equal ma towards the center, F equal ma. Why? Because uh, at this general point, it is still moving on a circular path. So the forces would be mg cos theta, mg cosine theta minus this reaction r equals m, since it has acquired a velocity v, so v squared over r being the radius of this sphere. Okay, so now what happens is that right, so sorry about this one, I had paused the video. Mg cos theta minus r equals mv squared. So this is the equation. Now what we can do here is that this equation consists of this reaction force as well, normal reaction. So let me choose another color here. So what is r? Now we have to find the height at which the particle will leave the sphere. So when a particle leaves the sphere, so now it is on contact with the sphere. This is the sphere and this is the particle. When it leaves, what happens is that the contact is lost. When contact is lost, there are no, in this case, we have a normal reaction. When the contact is lost, there shouldn't be any contact forces or any normal reactions. That means at the moment it released, R should be equal to 0. Moment of release. Right. So we can apply R equals 0 to this equation because we are looking at, we want to find the height at which it is released. So mg cosine theta equals mv squared over r. So m goes off and we get g cos theta equals v squared over r. Now what is v squared? We have obtained v squared here. V squared is 2g capital H minus simple h. So 2g divided by r capital H minus simple h. Now here, what is cos theta? Cosine theta is something that we have included into this. So cos theta is simple h over r. If you look at it, this is 90 degrees. So simple h over r. So g simple h over r. From on this side, you have 2g over r simple h. So when you take this to the other side, 2g h over r, and here you have 2g capital H over r. So when you add these two, you get 3g over r simple h and 2g over r capital H. So g over r cancels, this part cancels, and h, what we want to find would be 2/3 of the initial height. 2/3 of the initial height. So this is the final answer. Right. So thank you for watching.